Okay, welcome everybody. As always, we have a nice packed round here. I'd like to welcome John Matthis, and some of you may have wondered why he has two affiliations, UT Texas, or University of Austin, and Northeastern. And the reason is he is our guy, not quite yet. We hired him last year, but then John got a K award, NIH award, and with that award he had to stay at his postdoctoral institution for another year. And we said, that's okay as long as you come afterwards with the package of money. But that was not a decision criterion. You only got that after we hired you.
Yes.
So a few words about John. He has a very interesting trajectory, starting out with all the good things in life, that is with philosophy, at a liberal arts college in Oregon, Reed College, which is quite famous. And then following the philosophy training, he did a gap year and worked in Baltimore on autism. So I guess theory of mind, but then all sorts of other things with autism. And he discovered his fondness for science, applied for PhD institutions, and he ended up in Rensselaer with Brett Fagan. And I like to say that because Brett Fagan was my fellow graduate student at University of Connecticut. And so I have great respect and everything for your doctoral advisor, and of course for his whatever.
Postdoctoral?
Yes.
Yes.
So anyway, in the course of being here, contacting Brett, I invited Brett, and Brett said, I'm only coming to Action Club if my then graduate student is also allowed to present, and I'm always a little sort of cautious. But he said, Brett, don't be cautious, he's good. That was him. And about, 5 years ago, Brett and you gave a wonderful talk here at Action Club. Subsequently, I tried to get a postdoc, get John as a postdoc in my lab with funding. That didn't come about. So he ended up at a very good place, UT Austin, with Mary Hayhoe, and really turned that to his advantage in doing what he will present today. So very exciting stuff. I would like to say what I already said with Brett. So I think John is my academic nephew, right?
I think so.
Yeah. Right. And as we have family around, we have Ennio and we have Elliot, and I think you guys are kind of the
family.
Grand family. So you will get your mug as an entrant, and everything else is on you now.
Great. Thank you. I actually got one of these when I gave the talk however many years ago, and recently a friend of mine broke it. So it's good to have the replacement. So thanks for the introduction. Thank you guys for coming out. I'm going to tell you guys probably about a little bit too much of my research, so I'll try to pack it in. I'll probably rush through some parts of it, but it all sort of related to foot placement and locomotion, starting in the lab and then mostly looking at stuff that I've done in the real world. So behavior in the real world and sort of moving your body through the world requires you to sort of shape the forces that define your mechanical state. So people doing handstands, jumping over bars, the success and failure in those tasks requires the actor to apply the right forces to the environment so that their center of mass, or a general mechanical state, stays within the bounds that define success and failure on that task. And there's been, and a lot of people do that kind of work looking at the mechanics of movement and the biomechanics of behavior. But there's another aspect that I think often gets underappreciated in those contexts, and that's kind of the information that's required to succeed and fail in the natural world. Because it's not enough to just sort of have the right forces in your body. Those forces have to be properly correlated with the external world in order to be able to get you the goals that you want. So it's not enough for this tarsier to just sort of throw his body in some direction. It has to be in the right direction so that he will land on this tree and get the grasshopper and be able to go about his happy day. And it's that interplay between mechanics and information that I try to focus on in my research, in particular with regards to human locomotion. So yeah, so this is a passive dynamic walker. It's a robot of sorts that has no motors, no actuators, no controllers whatsoever, and yet it is capable of generating a sort of very human-like gait by putting it down this shallow slope. And the idea that sort of these sort of passive robots have been used to exemplify is the way that human locomotion is shaped by the physical dynamics of our bipedal body. And a lot of the way that we move is thought to arise from these sort of basic underlying physical dynamics. And there's been a lot of work looking at sort of how those dynamics shape the way that we move through the world. However, we were just having a conversation before, the question is, how does that type of sort of underlying physical mechanics apply when you're walking in environments like this one? So this is a bipedal human person, about 180 pounds of salty meat, sort of just tumbling continuously across this rocky terrain. And every 400 to 500 milliseconds, we'll see how these videos go. Every 400 or 500 milliseconds, he has to put his foot in a location that he's never seen before, and that can not only support his weight, but also will sort of properly shape his, the momentum of his body in order to keep him moving in the direction that he wants to go. These decisions have to come one after another. They depend on the decisions that were made in the past, and they were forced to rely on sort of basic underlying, he's forced to rely on visual information to make these kinds of decisions. So the question is, how does he do that? So anyways, a quick sort of roadmap for this talk. This talk is going to have roughly 3 parts. The first part, I'm going to be talking about gaze and the visual control of foot placement. I'll talk with some, a very brief overview of some older research, probably stuff that I talked about when I was here however many years ago, before going into the sort of outdoor kind of walking that in the previous video. That's sort of a nicely sort of well-packaged, already published kind of stuff. But that kind of sets the ground for the next parts of the talk, where I'm going to start looking at sort of doing computer vision, type of computational analysis of the information that's experienced during locomotion in order to understand how people might control their behavior in the natural world, and comparing what I see when we look at the visual stimulus experienced during natural behavior and comparing it to the kind of stuff that's described in the literature, and to see sort of what the relationship between those two things are, which we'll see. And then I'm going to wrap up with some very new stuff, looking at some sort of modeling types of research, modeling types of approaches I've done to look at more specifically how the kind of patterns of motion that we experience in the back of our retinas during locomotion might be used to help us move our bodies to the world with sort of the grace and stability that we do. Okay, so this is a increasingly old video from my dissertation days of an apparatus that I built to study visually guided foot placement in a lab. So this is a projector pointed at the ground that has been sort of calibrated and synchronized with a motion capture system so that you can sort of log when people sort of step on these virtual obstacles. And this was done to perform a series of experiments aimed to look at visual control of foot placement. So for a lot of them, the basic task was just basically walk from one end of the room to the other and don't step on any of these projected obstacles. But people are pretty good at doing that. In addition, we could sort of perform these experimental manipulations, really very choppy, where because we know where the person is and because the display is calibrated to the motion capture system, we can basically constrain the system so that the obstacles are only drawn when they're within a certain distance of the person. Then the question becomes, how far ahead does the person need to be able to see the upcoming terrain in order to be able to perform at the same level that they can when they can see the entire path? And the answer, again, just sort of blasting through this stuff, is that if you look at people's stepping accuracy, sort of how many times they collide with those obstacles that told them they shouldn't collide with, as a function of how big their visibility window is, we can see there's not really much of an effect of constraining vision until it gets to about 2 step lengths ahead. When you can't see 2 or more step lengths ahead, all of a sudden you start colliding with more obstacles and your foot placement becomes far less accurate. This is just one sort of measurement. We did a bunch of other stuff, all of which kind of circling around the same conclusion, which is that 2 step lengths of visual look ahead is sufficient for control of foot placement in this type of sort of cluttered terrain. So then the question is sort of what is special about that 2-step distance?
Can I just challenge you here? Because I think that has been shown by Patla and Marigold. So on the treadmill, is there any difference or additional insight by having shown this on the overground? Meaning, what are the subtleties of theirs and then your result, which I guess came afterwards?
Yeah, so there's a lot of stuff that winds up being consistent with this kind of result. The thing that the Patlas and the Marigolds of the world don't tend to do is I guess they're not around. They don't really tend to explain why those numbers come about. So it's this part with the skeleton and the pendulum and all that kind of stuff that I think is the kind of the part that adds to those stories. I mean, they had a lot of that stuff was sort of single obstacle. It was on the treadmill, so the sort of looking at extended stuff is different. But I think that one of the things that this work did that doesn't often happen is tying it to some sort of explanation of sort of why that distance is special, as opposed to just, hey, we found a number and that's where we are. It's not the most charitable way to describe other people's research, but it's okay.
So you might be getting ready to answer this one too, but along that lines, if you did that same curve and looked at walking efficiency or something like that,
yeah.
So does that exactly match the error curve, or are you making adjustments? You know, at what point do you just have to start making adjustments is the question.
Yeah, so in the interest of time, I'm sort of blasting through some of that stuff. I did do some mechanical analyses of sort of proxies to energetic efficiency, walking speed, and they all tend to follow that same sort of curve, where greater, when you can see more than 2 steps, it's really hard to tell the difference between a 3-step length window and a full vision window. But once you get less than that 2 steps, then you start seeing people's behavior start to degrade. And there's all sorts of interesting details about how that happens, but usually that line is right around the 2 steps, the 2-step lengths.
Yeah, I would also expect that how far ahead you have to have the information is how accurately you have to place your foot. So,
right. Yeah, and I think the next part where I get into the outdoor stuff will speak to that point of sort of different terrains demand different things, and people are very good at adjusting what they do to fit the specific demands of whatever task they're performing. So this, yeah, so yes, certainly. Okay, and yeah, so. Right, so 2 steps. What's special about 2 steps? A lot of the sort of there's a lot going on in walking. It's very complicated, but sort of a lot of the sort of basic mechanics of it can be described in terms of this inverted pendulum model, where you have this kind of very large, meaty mass supported over a single point of contact with the ground. And a lot of the work on walking and sort of the way that humans move is sort of based around that kind of model. So given that that's a reasonable way to think about movement, you can ask, what are the things that will determine the sort of passive ballistic trajectory of a walker during a given step? And it turns out there's, at the sort of highest level of approximation you can get, there's roughly 2 things. One is going to be the location of the base of that pendulum, or the location of that planted foot. And 2 is going to be sort of the initial conditions of that center of mass leading into that step. So basically defined by that push-off force, as well as whatever's going on with that stance leg. And those are the 2 things that will define the passive trajectory of a person's body during a step. And so then if those are the 2 things that matter, then it's reasonable to ask, well, when are those 2 sort of levers under the walker's control? And the answer is basically right around back here, right before that foot placement gets that foot lands, and before that push-off force is sort of enacted. And if those are the two things that define if those are the windows that define when those levers sort of are available for the control of the walker, then that defines sort of a relevant window for planning, and that's roughly 2 steps out. That's about all I'm going to say about this sort of era of my research life. There's a lot of publication on that at this point. But the long story short winds up being that we found through a series of experiments that when you're planning for a given foothold, the relevant sort of planning window for this footstep is roughly back here, sort of 2 step lengths prior to that step, and then kind of ending once that foot has left the ground. We call it sort of the critical phase for visual control and blah, blah, blah. Again, I don't want to go too deeply into that right now, but I just wanted to say that to kind of set the stage for this next part where, so right around here, I got a PhD and moved to Texas, and then I started getting interested in taking these sorts of ideas from the lab and bringing them out into the real world to look at this kind of stuff again. This is Shoal Creek Greenbelt, about a couple blocks from UT. Fun fact about Texas, that's the high water mark from a flash flood that happened a few months ago. Don't tell the IRB. And this very stylish fellow is wearing a bunch of equipment that would allow me to record both his body movements and his eye movements. Can't actually see what's coming up next, so I have to sort of rely on my memory of my slides. Oh. So he's wearing 2 things. One is this motion capture system. Sorry about the glitch style here. But you can see here he's wearing this sort of infrared blocking face mask, which is necessary for using eye trackers outside. And then this is the output of his of the eye tracker that's recording where his eyes are going on the ground.
So while we're changing it, there's also a question of time, right? It's 2 steps in space.
Yes.
2 steps in time. If you go faster, would it change? Can you slow down if you don't have as much vision?
So in the lab-based experiments, we did some manipulations to constrain people to walk at roughly sort of their preferred walking speed. The idea being that as you start sort of walking slowly enough that the steps are no longer connected to each other, then of course all that control mechanism kind of breaks down. I consider this to be a yeah. Okay. But long story short, it does seem to be somewhat robust to changes in walking speed. But that is to some extent an empirical question, which I haven't. So anyways, so I can talk over without a video. Yeah?
Well, if you prefer to talk, fine, because I know it's stressful, but if you're waiting, I have a question that's,
Sure.
again, about the time. Again, it's time and space. It seems like a long enough time, right? And when you're looking ahead, it seems like you really have to store something about multiple steps.
Yeah.
So my question is about memory.
Yeah.
You're kind of talking about information. So have you looked at,
Yeah. So
interference with memory or memory effects in this?
I haven't looked at like dual task kind of things or looking at anything.
Or seeing it and then masking it, and if you can make the memory go away that you stored and needed.
I have done things of stepping onto targets that sort of appear and disappear at different times, and you still see that kind of there's just a window where the information is more useful, that is sort of in that critical window, and one aspect of it can be explained kind of by the mechanics of where your feet are, but sort of there's an effect where basically you just seem to have a really hard time holding that information in your head for more than a second and a half, about a step and a half kind of thing. And it's not 100% clear why that is. We sort of assume it's some sort of visual memory decay kind of thing. But that's kind of one of the open questions.
It's not just decay, it's mass. You see that?
Yeah, yeah, it's matched, yeah.
it's masked by the previous, by the next view. And so that's why the memory dissipates much faster than like memory in a laboratory experiment.
Yeah, it's a special form that's matched.
It's fine. I'll just power through.
Yeah.
Sorry, guys. It's just a little kind of glitches like a super hip thing, so it's cool. Yeah. Just imagine it's perfect and clean. So yeah. Anyways, eye tracker, motion capture. It's IMU-based motion capture, so it's sort of a wearable suit. And then if you're willing to spend a number of your years of your life, you can calibrate the two things together and get a video, which is not, whatever, it's fine. This is the same terrain, same sort of rocks as before. And this is the data from the motion capture suit. And then this pink laser coming out of this individual's head is where their eye is pointing on the ground. And the dots on the ground here are where their feet are going to go in the future. So you can see there's this kind of like mad scramble going on as the person's walking through. You're walking over this environment that you've never seen before, and you have to kind of lay down this sort of epistemic path for yourself so that you can put your feet in places that will allow you to continue moving forward.
What do you mean by the points where the feet will go in the future?
So,
meaning from past recordings
yes,
or probabilities?
Past recordings.
Okay.
As you'll see, one could probably come up with a probability map of where the feet are going to go on the basis of the gaze data, and you could probably do a pretty good job of that, but I did not do that here.
So this is, you already played it once and you know where the feet are going to go. Now
Yeah.
you're playing it again.
Yes. And
As you are the subject, did you experience that you would do the same step, or is it all below awareness?
So I'm not this person, but I have been the subject many times, many times. I've walked this path hundreds of times. I cannot feel myself making these eye movements.
I mean, you're also not remembering that, oh, there's that big boulder and I just...
No, I could write essays about the boulders in this terrain. There's a big red one. There's one with the fossil on it. But in the moment, it doesn't seem to matter. And if you look at people go back and forth on this stuff, the 8th time over it looks no different from the first time. Possibly at the level of path planning, but for the level of foot placement, every decision seems to be made on its own.
So how different was between subjects, the path? Like they actually went to more or less in the same spot?
You see these kind of bifurcations that happen, where there's sort of corridors that people like to go around, and sort of less preferable to go other ways. But I haven't looked at that in too great of detail. The nature of this recording is looking at that kind of path between subjects is kind of tricky, not impossible, but kind of tricky. And I just haven't put much time into that. But there does seem to be, if you plot them all on top of each other, you can see these sort of corridors that seem to be places that people like to go.
So you could build a trap in that you have the subject go over it 50 times and then you rearrange one boulder
Yeah.
and see whether
And
it's
see if that
online
matters.
computed
Yeah.
or whether the person just keeps stepping the same path.
One could do that. Yeah. Yeah.
Did you check how their path changes as a function of their velocity? I don't know if your IRB would allow them to run through this terrain, but I feel like having to run outside, I feel like I
Yeah.
require less stable trajectory.
I did not do anything with walking speed. I just walk at a comfortable walking pace. Average speed was I think 0.9 meters per second on these rocks. Running would be good, but I haven't done that.
Along those lines, I also wonder if there's a correlation between speed and memory. If you go slowly, you might rely more on having walked the path before. If you're pushing the pace,
Yeah.
then you're not going to have the time to deal with it that way. You're just going to...
Yeah, and the forces are much higher, so your control authority is a little bit less. All good questions, often the answer is, have you done this? The answer is almost always no, but they're almost always good questions. So, okay, so I see. Okay, I'm gonna I'm going to push through this stuff pretty quickly because I want to get to the latter stuff. And this is all published anyway. So this is rough terrain. Everything I've been showing you is rough terrain. This is by far my favorite terrain. But we also looked at other terrains, such as medium terrain. In this, it was still rocky. There were still rocks, but it wasn't the same kind of boulder hopping thing as the previous terrain. So slightly easier to find footholds in this environment, but still, have to pay attention. And then also flat terrain, which is sort of this packed earth trail where you can more or less put your feet wherever you wanted. And so then the question is, how do walkers alter their gaze behavior and stepping behavior to accommodate the specific demands of each terrain, sort of speaking to your question from earlier, possibly. So to look at that, we wanted to look at the relationship between these pattern of gaze on the ground and the steps that came up after it. You're looking at the ground, second and a half or so ahead of you. Sometime later, you put your foot in a location. What is the relationship between those two things? This is one walk down that path. The pink line is the center of mass trajectory. The yellow blobs is the gaze density. If you plot everybody on top of themselves, they tend to follow here, but then sometimes some of them will go that way. A lot of fun stuff happening there.
So that is repeated trials or a single?
This is a single trial. Yeah. One center mass trajectory here. Yeah. So then to look at that relationship, I first took all of the sort of gaze data from a particular terrain. And you can imagine each of these blobs comes from, the eye tracker has frames, and every frame is a data point where the gaze vector sort of pierced the ground plane. So then what you can do is you can take all of those points and subtract out the location of whichever foot was planted at the time that gaze vector was, that sort of gaze point was recorded. And if you do that, you get this thing that kind of looks like this, where origin is now the planted foot. And you get this kind of blob of gaze data about 1 to 2 step lengths ahead. And so then if you do that for the flat, medium, and rough terrain condition, you get something that looks like this. So just to orient you to this plot, the red triangle is the planted foot. The orange is where that is the foothold n+1, n+2, n+3, n+4, right? So then what you can do from there is instead of aligning gaze to whichever foot was planted, you can align it to whichever foot was coming up next. And if you do that, you get this kind of shape. And you can basically just keep realigning all the gaze data to the sort of upcoming steps. And you can see that the gaze probability distribution sort of changes as a function of which foothold you're aligning it to. And something that pops out here is in the medium and rough terrain, gaze sort of has the highest peak when you align it to the step n+2. So where your foot is going to be 2 steps into the future. You can sort of plot that here. So highest peak for medium for rough and medium when you align step n+2. Whereas in the flat terrain, that blob kind of shifts down the origin, but doesn't really change shape at all. Which means that although people are looking at the ground, they're not fixating their footholds in the same way that they do in the more difficult terrain. So although gaze doesn't have that same sort of correlation with upcoming footholds.
Is the rough terrain n+1, its shape is a little different from the others? That has anything to do with something?
So there are interesting differences for the rough terrain. Specific n+1 happened because in that terrain, people would occasionally look at the place that their foot was currently going, whereas in the medium terrain, that happened very rarely. In the flat terrain, it never happened at all. So that's why you get this kind of, in a full disclosure, there was like 1 or 2 subjects that did that a lot, which is why this is not a particularly smooth. Someone asked about individual differences. Mostly very similar, but you did get some sort of people that like to look at that n+1 step.
Is the density of the gaze also a proxy for how long they are looking or not?
Yes, it is.
It is, okay.
Yeah. Yeah, so
Like how often I'm counting your density as how often they saw, but how long in a particular gaze they kept looking at the same.
across a given recording, it's a density distribution there. So I'm not cutting it up by fixation or step or anything like that, but
Just
samples, yeah,
so it's
exactly,
time
yeah.
and-
Yeah. So it does. These blobs don't sum to one because they occasionally looked away from the ground, but yeah, yeah.
I was just thinking, in naturalistic scenarios, right? You look at the birds and
Yeah.
bees and so on.
Yeah, yeah.
And when you then get back, are you immediately focused yet again on that N+2, or is it like a search process?
So in this terrain, you looked at the ground about 60% of the trial, which is probably an overrepresentation of what you need. In this one and this one, I think this was 92%, and this is 96%. So in this terrain, there's not a lot of free cycles to look at birds and turtles and stuff like that. I have tried giving people alternative tasks in this terrain. I've tried doing it myself. It's very hard to do that while maintaining walking.
But the medium terrain, right? That would work. And my question is just how much do you have that, call it internal knowledge, where to look immediately after wandering?
Yeah,
To what degree is it sort of the result of a continued?
Yeah. So again, that's on the list of. So I haven't really done anything that looks at sort of individual time points. I've only ever looked at sort of aggregated data. For obvious reasons, that's kind of where you start. That's where you get the easiest statistics. Going back and looking at sort of, okay, like, so when people stumble or something like that, what happens then? Like those are questions that one could answer with this data, but I just haven't looked at it at that scale.
Are there any sex differences in any of these measures?
So it's all scaled by leg length, and that actually normalizes for gender differences pretty well. The differences in height of my subjects was significant. I mean, not in the statistical sense, but men and women actually, like, women tend to have longer legs than men. So when you scale by leg length, it actually makes a lot of those differences go away. I don't have enough subjects to do any proper. It's like 6 subjects. So, but it wasn't really a part of the study, but it was sort of interesting that the guy like this and the girl like this wound up having similarly sized legs, and everything is being scaled by leg length. So it's kind of washes out.
Gender difference other than biomechanical?
I expect sex difference, not gender difference.
Yeah, I know.
because
okay.
the pelvises of men and women are different, and also their caution might be there.
Yeah.
The uncertainty they're willing to tolerate might be different. So.
Yeah, I don't have that many subjects to be able to tell that kind of thing. All my subjects were young, healthy, capable individuals. And there were some differences, but not to the scale that I could see anything of interest.
Yeah, how many times did they stumble or fall? Is that like specific data we're going to see, or?
No. Sometimes they did. It wasn't something, nobody ever hit the deck. But
Worried about the equipment.
the equipment's pretty robust. The computer's on their back, so. Yeah, exactly.
Wait, can you tell when they put their foot somewhere and then it doesn't end up where they want it to go, like it slides?
You can see people sometimes a rock shift or something like that. But yeah, I haven't looked at people. That's a question. Like, when you do stumble and your foot goes somewhere, like, are you just guessing and hoping, or is it, I have not looked at that, but it's always fun because people see this like, oh, what about this? What about this? It's like I haven't. It's kind of nice how little of this data set I have milked. There's a lot of stuff in there that I just haven't gotten to. All the data is online, along with the code to analyze it. Okay, this is all fun stuff. I am going to completely skip the rest of this part because I want to talk about this part. Fun stuff, wonderful results, nice, consistent, theoretical, blah, blah, blahs. It's all in current biology. Check it out. It's okay.
Now you need to ask the question that is the most annoying question. You haven't read my
I worked so hard on it. But no, it is. I mean, the data is all online with the code to analyze it. So if these questions are all, you can explore them yourself. Okay, so. So that was studies. So that study basically was looking at sort of how, like, what do we do with our eyes, and sort of what is the relationship between our gaze and our foot placement, and looks less to say about what the information we're using actually is. So this next part of the talk, I'm going to be looking at sort of aspects of the visual stimulus that have been classically thought to be a part of the visual control problem, and start sort of quantifying those aspects of the data that were recorded. So I think there's not a ton of vision people in the room, but sort of classically speaking, if you go look up visual control of locomotion, the vast majority of research on the topic relates to optic flow. Going back to good old James Gibson back in the 50s and 60s, who noted that as most of the world is stationary, and yet we are not. So as we move through the world, we experience patterns of motion on the back of our retina, and that information can be used to sort of figure out certain aspects of the environment. And specifically, Gibson liked to talk about the idea of this focus of expansion, which is the idea that as you move in a direction through the world, everything will sort of expand outward from a central point. And there has been mountains of literature looking at how one could use something like the focus of expansion to control something like heading. So having been raised in a nice Gibsonian household at Rare RPI, I wanted to see what this sort of information looked like during natural behavior. So to do that, focus of expansion, FOE, that kind of thing. So to do that, this is not going to cut it with this 640 by 480 1995 VHS looking video. You can't do the kind of analysis you want to do on that. So I upgraded my eye tracker, and this is the new one. And isn't it nice? It's not even jerky. So this is a Pupil Labs eye tracker. It is both the cheapest and best mobile eye tracker you can buy. Pupil Labs. Open source, which winds up being very important for this project. 1080p video, 100-degree horizontal, so it's a very wide field of view. And it's a binocular eye tracker. So this skeleton has now 2 lasers shooting out of his face, one for each eye. And they're actually completely independent, so the fact that they're pointing in the same direction is a nice sort of confirmation that the thing actually works. So then what I can do is I can take the video from this eye tracker. I can also put it in this sort of spherical pinhole projected retina-centered view. I will get back to this later. But to start, I want to talk about you can just take this video and run it through some computer vision algorithms to estimate the visual motion in that scene. That looks a little something like this. And by the way, I'm using the same recording for pretty much everything on out, but I have a lot more data than just one walk up and down. So this is the result of, I think, the deep flow optic flow estimation algorithm, which spits out a motion estimate under each pixel of the recorded video. I'm showing just a subset in these sort of blue arrows here. Within this video, within this sort of vector field of visual motion, I want to be able to estimate where the focus of expansion is. So here is one frame from that video. And you can sort of, with your big human brain, see that there's this sort of focus of expansion right here. But we want a way to track that quantitatively. So what you do for that is you take this vector field, and you note that this point here is sort of acting as a repeller, sort of pushing things away from it. So you multiply the whole thing by -1, and it becomes an attractor. Then you take a grid of particles, and you set them to drift along that negated flow field, and they all wind up in this location here, which you can then say that is your focus of expansion.
And that's not the same as gaze direction.
Not at all. It's this analysis has no idea where your eyes are pointing. Yeah.
Even by the motion, direction motion.
Yeah.
This is on the picture plane.
Sorry.
It's on the picture plane.
Yes, and we've done all the calibration stuff you need to be able to convert from, pixels to millimeters to angles and all that kind of fun stuff.
Do you do any 3D?
Not yet. We do have a stereo camera,
That
and
would be interesting.
it would be, and it's on the list, pretty high on the list. But one recording session from this generates about 80 gigabytes of data. So
Yeah,
I'm happy to double that, but it's there's other work to be done as well. One subject after analysis is roughly 2 to 3 terabytes. Takes about a week to process, but it's fine. So then you can take this analysis and apply it to every frame from these recordings and get that track that focus of expansion, as well as those these sort of streamlines. So these white lines are the paths that the particles take. Learned recently, this is also the same as the integral curves of the vector field, if you are into that kind of thing. So before I do that analysis, let's again go back to this what's in the literature and guess what would the literature predict this kind of thing looks like. And this is not like a small pile of literature. This is a large, vibrant field for the past 50 years. And they always have in the first paragraph of their paper, optic flow is used to control heading. The focus of expansion is used to control heading. The idea being that this sort of point of expansion is some stable thing in your visual field that you can use to figure out where you're moving in a scene. I have written some of these papers. And yet, when you go and actually do this analysis, you find that that is not actually what you see. So I'm going to slow this down. So this is the same thing being played at 1/4 speed. And you can see that the focus of expansion is in there sometimes. There it is. There it is. And it is sort of zipping through the scene, but it's happening at a very rapid rate. Yeah.
What frequency are you sampling at?
This is 30 frames per second. We've done it at higher frame rates too, and it winds up being the same.
Can you comment, how much of what you're sampling is pursuit eye movement and how much is the
So again, the focus of expansion has no idea what your eyes are doing. This down here is almost entirely fixation, but because you're moving, your fixations wind up having this slope shape because you're VORing, your vestibular ocular reflex. Yeah, Mary has beaten that term out of me. It is not a pursuit eye movement because it's not tracking a moving object. You're stabilizing against your own movement. But it's
probably a combination.
it took me a while before Mary beat that term out of me. But these are all fixations.
But it's head-centered, right? So you could ask the question, how much of it is related to head?
Right.
You also do head.
Right. Yeah, and that will come up. But the literature says that, and there's a lot of stuff out there, and I'm going to get to that in a second, that what Gibson told us is that it's the head-centered focus of expansion is what we use. And a big part of that mountain of research on this topic is how can we correct for the visual motion imparted by our moving eye in order to recover this stable head-centered optic flow field. But when you actually look at the data, the head-centered optic flow field is not stable at all. Yeah.
But so are you the first one to measure it? You're the first one to measure it in this rough terrain, but has it not been measured in a lab environment?
Haven't seen it.
No, it's been measured in a controlled lab environment where you don't have this kind of random
Yeah.
evolution, and that's a big thing.
Yeah.
It's huge.
How does it change when it's like the flat terrain?
So I have looked at that. I will show, I think actually, is it the next slide? Oh, no. I'll get back to that in 1 second. Okay, so we have all these questions about, is this a valid way to measure the focus of expansion? One question you might have is this wacky video analysis capable of producing a stable focus of expansion, or is it just too noisy? Took this nice Phantom 4 gimbal stabilized camera drone and moved it up and down and in a straight line, did the same analysis, and the focus of expansion is nice and well behaved. So it is possible, so if the focus of expansion was a stable object in the visual field, it would be possible to measure it as such. But when you actually look at what the visual reality of the head moving through the scene, that's just not what you see.
But you have all kinds of, I'm sorry.
No.
But what happens if you correct for the orientation of the head?
Yeah.
So if you correct, so basically stabilizing like this.
I don't know what I'm looking at there, but if you measure the orientation of the head and subtract it from.
So that is effectively what we do when we fixate something. That's the vestibular ocular reflex.
Right.
It basically counter-rotates your eye to maintain fixation on objects in the world. So that's what I've done here, is I've taken this, projected it onto a sphere, and then rotated it according to the measured eye movements. And if you do that, then you get this nice stable thing.
Okay, but the eye movements there is the VOR, but the eye movements are also doing something else.
They will occasionally saccade, but they're either saccading or VORing in this environment. We're physiologically incapable of doing anything else.
You could talk about it.
Yes, we could.
I mean, but there is evidence that you can do other things. We can talk.
Yeah.
Is the when this in the video center, when it spirals, is that just like head rolling, or is something more sophisticated than that?
Seems unlikely I'll get to that, but I'm going to try to get to that.
Oh. If we let you.
If you let me, yes. So anyway, so I recorded, so this is the rocks. I also looked at flat ground and free viewing, or just fixating off into the distance, or looking at the ground. And I recorded the velocity of the focus of expansion in all of those environments. And it actually winds up being very nicely similar, where the average velocity of the FOE is about 300 degrees per second during natural locomotion, which basically means it's, before I get to that. And then again, I doubted that maybe this is not a real valid way to measure something. So I found these equations from 1980, where you sort of plug in the 6 degree of freedom velocity of the head, and that will sort of generate a flow field. And I took the data from the motion capture system and fed it into those equations, recalculated the focus of expansion, and this is what you get from the video. This is what you get from the motion capture. Completely independent measurements. That's just what it is. And so basically, the strategies that are described in the literature for how we use optic flow to control our heading simply cannot be realized on the basis of the stimulus we experience during natural behavior. It just wouldn't work. So someone asked earlier, so how did they get it so wrong? How is the literature such a poor representation of what we see during natural behavior? And the answer goes back to this little squiggly yellow stylus coming out of the person's head. Can anybody guess what this is? It's the head velocity vector. So as you move through the world, your head follows this. I think this is the right one. So this is head acceleration. X, Y, and Z. X is forward, Y is up. Sorry, Z is to the side. Each little blue line is one step, and the vertical line here is toe off. So this is the double support phase. Vision scientists assumed that walking is well approximated by constant velocity straight line motion, because why wouldn't it be? And so and if you had constant velocity straight line motion like that drone, indeed the focus of expansion would be this nice stable feature of the visual scene. But if you actually look at what the head really does during locomotion, that is a very poor approximation. And so this velocity vector that defines where the focus of expansion is in the visual scene is zipping around all over the place. And because those small angular distances are projected into this visual environment, a small angular difference here leads to a huge displacement of that focus of expansion.
Is it velocity or position?
This is, it's just the velocity vector. It's scaled so you can see it. It's just, it's basically just done to show that the head velocity just changes a lot during a step, and that although there is some pretty nice periodicity to it, there's also a lot of noise.
But I was just thinking, noise, or it looks like a wand.
Yeah, right. Yeah, noise is not the right word.
Yeah.
It's a complex relationship.
And the periodicity comes from the stepping, mechanically induced.
Yes.
But then around that, there may be visual exploration.
Right, and you can see, it's harder to see in this, but you can see the way that these sort of integral lines kind of curve around the structure of the rocks and the structure of the scene. There's information in there that I think is important. And again, blasting through this next part here, this is kind of the bummer part of the talk. Like all this literature doesn't really help us with the real world. But there is sort of a, Return of the Jedi part coming up, where when you actually look at this data and you look at sort of what kind of structure comes out of it, you mentioned the swirling that happens. There is actually information living in, maybe not in this part of the plot, but over here in this retinal optic flow, there's a lot of good structure that I don't know if we do, but there's interesting structure that correlates with aspects of movement that we would really want to have access to control our movement through the world. And I have a little bit of time. Yeah, right. And traditionally speaking, that's eye movement. It's been called the eye movement problem, where the question is, how can we correct for these horrible distortions that our eye movements cause to recover this nice, stable, head-centered flow? But now I'm going to look at, maybe that's looking at things backwards. Maybe the retinal optic flow is the place where all that good information actually lives.
Just to be clear, what you just said also explains why in the lab they didn't detect, because mostly in the lab the vision was not too rich to explore and people didn't have much head movement. Is that right?
So this is a bit of a subtle point, but in the lab-based, so I don't think anybody did their research wrong. I think all the empirical results are correct. But often what they did in those studies is they would give people these trajectories, and then they would induce these flow fields on top of those to simulate eye movements, and say, can the person still recover their world-centered motion from these corrupted flow fields? And the fact that they could, people can, has been used as evidence that people must be able to correct for their eye movements to recovered head-centered flow. But what I'm actually going to show is that this information is embedded in this information. You can determine your world-centered velocity from your retinal optic flow. So that's why I think those results existed. Sort of just a misinterpretation of what people were actually capable of doing from retinal flow. So again, changing pace, changing something. So I wanted to basically have a handle on what those, basically what's going on the back of the eye during movement. So I started making these sort of simple models. This is when I got the job. So I started just playing around with sort of fun videos and models and geometric stuff. And it wound up bearing some nice fruit. So this is just a very simple two-dimensional eyeball moving while maintaining fixation on this point on the ground. And these are just points on the ground that are projected through a pinhole pupil onto the back of the eye. This is a picture of that eye, and so you can see how the red dots in the lower visual field and the blue dots in the upper visual field sort of change their position across the course of that movement. And then this is sort of how those retinal positions change and how those velocities change over the course of that movement. You can also plot this same thing in an eye-centered reference frame, and you can see that fixating a point on the ground and moving towards it is equivalent to looking at a plane that is both moving towards you and rotating at the same time. It's one of these things where there's a lot of literature on rotating and translating planes, but just sort of randomly assigning those translations and rotations, not considering the fact that there's sort of a special case of that. That is what happens when you fixate a flat object and then move towards it. Then again, just sort of fun pictures, which I will talk about in some. I'll say more things than just pointing at them in a second. This is just basically looking at a surface of those retinal velocities over the course of a movement. And just to point out that it's so this black moving line is the same as this one. And then these axes are, let's see, so the blue and the red corresponds to upper versus lower visual field. And then the cyan to magenta is early versus late. And then the Z, the height is retinal velocity over here. And then this is going to be divergence, which is just retinal acceleration. And the point of this is just to show that there's a structure here. It's more complex than just the focus of expansion, but just in the same sort of, basically just adding eye movements to Gibson's world and thinking about what is the sort of structure of retinal motion you experience when looking at when fixating something and moving forward. There is a structure here, and perhaps we can exploit this structure to determine things about the world that we need to control our locomotion. Here is one example of something that comes out of that. So you take this circular eyeball and replace it with a spherical eyeball, and now project it onto this ground plane. And here's something that pops out. So if you are fixating a point that is directly on your path, there's no rotation at that point. There's expansion, things like that. If you are into things like divergence and curl, there's zero curl at the point of fixation. If you are fixating a point that is to the left of your travel path, there's a counterclockwise rotation, which is also a positive curl. If you're looking at a point to the right of your path, there's a clockwise, or there's this way rotation and negative curl. So if you were able to determine something like curl at the point of fixation, which there's physiological reasons to believe that that would be something that we could do, you can know immediately if you're moving to the left or right of the point that you're fixating purely on the basis of that retinal information. And that would be a useful thing to know. Moving a little further. So basically then you take this spherical eyeball model and you attach it to that skeleton from the previous video, and you do that same kind of thing. So don't worry about these colors yet. Same skeleton, same recording. Now this eyeball here is that spherical eyeball from the previous time, and then these dots are sort of just a grid of dots on a flat ground plane projected onto the back of this individual's eye. The eye movements have been idealized, so the fixations are sort of pinned to the ground, and you get this pattern here. And so then if you look at the curl on the back of the eye, you can see that it sort of changes sign from positive to negative as this white line here, which is the person's velocity vector projected onto the ground, sort of sweeps back and forth across the point of fixation. This field, which is just okay. So you take the vector field, you apply a curl operator to it, and you get this sort of curl field, which is either blue if it's positive, which is counterclockwise rotation, or red if it's negative, which is clockwise rotation. And you take this, you project it back onto the ground, and then that gives you this sort of curl field. And you can see that maybe you can see, that the sign of that curl changes signs depending on which side of the fixation point that person's velocity vector is going. Okay.
This is a single eye, right?
This is a single eye. I have done.
Earlier you had retinal center that was also in the same one single eye.
So it's called the cyclopean eye. So you just sort of put one eye in the middle. I also have done this analysis for 2 eyes. When you do that, you get an interesting thing where because the eyes are slightly offset from each other, you get 2 slightly offset peaks on this curl field. And I'm working with some people at UT who are looking at basically the relationship between that sort of binocular information and optic information, which could be used to give you sort of a nice.
But 2 eyes is more or less 2 copies of the same.
2 copies, but offset.
Little offset.
Yeah, and that little offset winds up mattering. Because basically, if you're fixating a point, if you're fixating a point that's directly.
Would be red for one and blue for the other.
Exactly. Yeah. And if you're looking to the left, it's going to be slightly more red for one. Yeah. And perhaps that's useful. Now, perhaps you've noticed that this side of the screen is white. You can do that same game that I talked about for curl with divergence. So curl is roughly speaking just a measure of rotation for a vector field. Divergence is roughly a measure of expansion and contraction. If you're moving, looking at a flat wall that's parallel with you, you'll get sort of this expansive flow field. If you project that onto the ground plane, you get this interesting effect, where, let me just pause this for a moment. Yeah. So as the person is fixating here, points that are near him are expanding more rapidly. The points that are far away. And again, if you sort of map divergence onto this color map here, you get this interesting shape where there's this sort of peak here, and then it kind of falls off there. Now, this green circle is just an isoline of whatever the value is at the point of fixation. You just draw an isoline of all the divergence that matches that point. And then you get something very interesting popping out. So if you project that point onto the ground, and then you put that person's velocity vector, and you project that over top of it, what you'll notice, oops. Oh. It is 2 steps ahead because that's where people look, but but even more than that, that velocity vector always passes through that foveal isoline. And so what this means, and this is very exciting when I realized this was not a prediction, this was a discovery. It is possible to determine your body's world-centered velocity vector directly from retinal optic flow. And if you're a person whose mass doesn't change over the course of a step, that's also the same thing as being able to determine your momentum vector on the ground plane directly from the pattern of activation on the back of your eye, which is exactly the information that you would need to be able to determine what would happen if you put your foot here versus there. So what that means is that directly from this retinal optic flow field and very simple curl and divergence sort of local operations on each point of that flow field, you can determine both what your relationship is to the point of fixation with this curl, and also your own body's world-centered velocity vector directly from retinal flow.
I'm just curious, is there some simple way to see why the center of the divergence field is little below usually the...
It winds up being, so Jan Kundering did a bunch of work on this in the 70s. He was a brilliant person who was a terrible writer. So there, yes. So there's a student, Carl, in my lab who has been flagellating himself by working through all that math. It winds up depending, it flips from below to above. Depending on the angle so basically it flips from the bottom to the top when at 45 degrees. if you're moving in a straight line. When you go up or down, it scales a little bit. But the attitude of this circle within the visual, within the retinotopic map or whatever, is dependent on how far you are from that point. So it winds up being like a complicated geometric thing that I honestly don't fully understand myself, but it does actually fall out of the math that Kundering published back in the 70s. It's just, what's that?
And your eye height would be.
And your eye height, yeah. So basically, it's if you're moving in a straight line, this point is close to 0 when you're looking at a point that is your eye height away. Yeah.
Is this result dependent on the terrain roughness?
It has not. I have done a little bit, nothing in here right now, of looking at the way that, so this is flat ground. Once you put structure in there, interesting things come out of it. You get interesting behaviors. Kundering actually did some stuff on this too. But you get, basically you can, these sort of operations on a flow field that has structure to it are informative about that structure. These are really nice sort of structure from motion cues. And if this talk was a month from now, I might have more to say about that, because that's exactly the kind of thing you would want from this. You could imagine having a person walking might have some sort of baseline expectation for what you would get from a flat ground, which could then be used to enhance the motion signal that you get from here to sort of increase your sensitivity to those deviations that were caused by structure. And I think that's kind of the point that that I want to end on, is that the literature on this topic suggests that really, I think, does optic flow a huge disservice. By talking about it in terms of heading and the focus of expansion, it's really suggesting that optic flow is being used for what's honestly a pretty boring part of the locomotor problem. Heading is just not a very hard problem. Am I going to pass to the left or right of that flagpole down the road? Like, who cares? Am I going to be able to put my foot on the right geometric shape to continue my body moving forward? That's kind of a problem worth solving. It's a problem worth having dedicated areas of our brain that process optic flow and visual motion. Determining the 3D structure of the environment around you, that's hard and that's important, and that's the kind of thing that really is going to define success or failure for a given organism. So I think that this stuff is really just kind of scratching the surface of what of the kind of information you can get from this kind of this kind of visual information, and I'm sort of looking forward to continuing to pull on these threads. Yeah. So thank you. I should say, so this is my postdoc advisor, Murray Hayhoe, and this is Carl Mueller, who's done a lot of good work on this stuff. Yeah.
Really exciting stuff. I'm just amazed, really. From that same lab, are you able to see anything like foveations in the center of where you're going to put your foot versus at the edge of something you want to avoid? Is that even available in your...
It's not, one could do it, but it's not an easy problem. Basically the big hamstring there is this flat ground plane. It's very difficult to get, because you can look at it and see, oh, well, this is a rock and yada yada. But once you get here, it's hard to relate the footsteps to that. The stereo camera, and there's one of the sort of possible steps down the line is to get a stereo camera on the head, which will allow us to do a 3D reconstruction of the terrain, then have a 3D map of this environment in this reference frame. Once that's done, that's when I'm hoping to do more of that.
Could you, with all the information you have about the head, with all the information you have about the head, could you do 3D reconstruction from motion?
I have, so like SLAM.
Short instance when the foveal point's not changing that much. You might get sort of differential.
Yeah, so like a slam kind of thing?
Yes.
Yeah, one could. I have not. It's something that one of the nice things about working in this sort of computer vision-y space is that there's been a ton of work done on it. And people just kind of publish their code. OpenCV is an amazing resource. That's how I did most of this stuff. But it's not always exactly plug and play. And so I've done a little bit of work, and by I mean I told Carl to do it, in trying to implement some of these SLAM algorithms to do exactly what you're talking about.
This would be a very cool capstone project for DC students once you're here, so we can talk.
So one could do it with monocular. It'd be easier to do with binocular data, but all the data is there for sure. Yeah, I think you were first.
Thanks. Thanks a lot for your talk.
Mm-hmm.
Do you think it might make use to decompose this problem to simplify it into virtual reality to watch how people actually go through 2D arcades, like labyrinths and those appearing obstacles, trying to maneuver and find their way?
Yeah, so there's Bill's lab has done some stuff. Bill Warren's lab has done some stuff like that, and a part of getting this nice big lab space is that all my postdoctoral work has been in this outdoor environment, which is great, and I plan to keep doing it, but you don't really have much control. So I'm excited to be able to go back into the lab and take some of these things and actually start designing experiments where I can start twisting some of these knobs, specifically to start looking at, okay, well, outside it looks like people are doing X, Y, and Z. Let's design an experiment that tests X, Y, and Z, and then you can kind of like develop a nice little ecosystem of relating real-world semi-observational research to lab-based controlled experiments. You're yes.
So thank you for the great talk. For the last part of your, again, a question for the green thing coinciding with the direction of the velocity. Do you think they just correlate or coincide, or is there any causal relationship?
There is some. It's purely geometric. There is some causal relationship there. Jan Kundering did the math for it. It's just a matter of decomposing what he actually was writing. But it's a geometric thing. It has to be that way because of the laws of optics. I don't fully understand the math behind it, but that's something that's being worked on. But yeah, it's something about the geometry. You can see this before the movie happens. There's something about the geometry of a fixating eye in a flat plane that generates the divergence pattern that has this feature. And one thing that our brains are really good at, it's exploiting those kind of causal regularities between our movements and the pattern of stimulation that generates. But that's the million-dollar question, is sort of where it comes from.
Repeat the questions, because sometimes the people are not very loud.
He was asking if,
I heard that one, but
yeah, in general, okay, yeah.
A couple of things. First of all, I was wondering whether the fact that you have rough terrain that has occlusions would actually improve the aim-point estimation of the person in addition to the flow, the vision flow, because that could be. So there's two forces working against each other. Right? Rough terrain has to put more constraints on you, but at the same time gives you more information.
Yeah.
Repeat that question.
So he's commenting on the interesting features that a rough terrain with a lot of occlusions would have on the optic flow field. And there is indeed, I wish I actually had thrown some of that in here, but if you color map the optic flow, you can see that sort of like on the edge of a rock. Right. So for example, if I'm moving towards this thing, there's the same movement here that there is back there, but because there's a difference there's a difference in magnitude, and that shows up as sort of a hard contour in the sort of the magnitude of those optic flow things. And so you do get some really interesting features at those sort of occlusion boundaries that I think absolutely would be something that, and that's something that our visual system does take advantage of.
The other thing I was going to say when you were talking about the VOR versus flow, here is a thing. VOR is actually depends on where you're looking. If you're looking close, you have very different gain. Right? In fact, I can remove VOR. Usually, you should do it with a cigar. But if you look at this, you don't have VOR, right? So it's not just simple VOR.
Yes,
It's more complicated.
It's always more complicated. Yeah.
My question really related to that, right? And I think it's fantastic, right, that you recast this question. Well, how do we compensate for these crappy eye and head movements? And you've shown that, in those frameworks, you get information directly. That's really awesome. But I'm just unsure about how you're kind of calculating, one thing. It seemed to me that you had one set of calculations that were kind of dependent on the eye being perfectly fixed, namely perfect VOR, right? And then another set of calculations that was based on compensating for head movements. And then you showed two curves that looked kind of the same, but I couldn't read the scale on the probability densities, right? And they were a little bit differently shaped, and it looked like the peaks were a little bit different, which is saying that the VOR is not perfect. And so this kind of gets back to the question that you really ended on that was really awesome. So the success, right, of having neural systems that can decode the pearl and divergence, right, is really defining the success of the animal. But between that is still, the gain of the VOR, which you just brought up, is kind of a critical question. So am I right about those it looked like there was difference when you calculated?
What do you mean, like the focus of expansion velocities,
yeah, you
or
two probability density plots over here? One of them was based on the head velocity. The other one was based on an eye being perfectly.
This one?
Yeah, so I can't quite read the.
They are different, and part of that is actually just Carl did this one, I did this one. I think he used a different number of bins. And I didn't have time to update it. This doesn't have VOR in it, but you're not wrong. I mean, for these videos here, we've idealized the fixations, and for the simulation, I idealized the fixation to assume perfect VOR. But it's actually not, like, we know VOR is pretty good, but we don't know how good. And these eye trackers are not perfect. So it's very hard for me to determine if you have a fixation and you see some movement, how much of that is due to the VOR not being perfect, how much of that due to the eye tracker not working very well. And these are sort of questions. So on the ever-growing list of possible experiments, one of the things I want to do is look at sort of, how good is VOR? And one theory I have is that it depends on what you're doing. Like if you're walking and trying to figure out, can I put my foot on that rock? Then you probably don't really have to clamp it down that hard. If you're walking and trying to read some small text on the ground, then you probably have to clamp it. Then you probably have to and probably would clamp it down harder. Michele Rucci at RIT is doing all these, tiny sort of 15 arcs minute fixations, and sort of seeing that when you have people do tasks that rely on that, people can fixate at that scale. Do we do it here? Almost certainly not. But it's an empirical question. And one that's hard to get at because of the limitations of the technology that we have right now.
Yes. So my question is related to the second part of the problem, which is, the information that you extract helps you decide where to place your foot, but what about how much force to apply? Does that help in any way? Is that related to the momentum vector you mentioned?
So I don't have a good way to measure that, but that's obviously important. The roboticists talk about the friction cone. So for a given friction, you can apply your force at a certain angle before slipping. In Texas, this is all limestone. It gets slippery when it's wet, but if it's dry, it's if you're walking in the red stones of Moab, it doesn't get slippery when it's wet. Like, how do we determine these things is, I think, an open question. I think at the level that I am thinking about it, I assume just people can solve that problem, but it's unknown, and sort of the degree of they call it pre-flexing, like you can change how stiff your leg will be when it hits the ground depending on what you're doing. The well goes all the way down, and I'm really just looking at the surface level right now. I think, yeah.
Thank you. So first thing, I don't know if everybody's familiar with VOR, so can you spell out what it is?
Yes.
And so the second thing is more related on project. So I was wondering if I mean, locomotion has been modeled with inverted pendulum. So what could be the effect of this finding on the modeling? So how would you model out how this new information you gather affect the inverted pendulum model? And it could be tested in an environment in which you have a constant velocity. So your flow is, I mean, then your head is moving at constant velocity on maybe on a treadmill. You will still have all this rounded flow, and how would you, I mean, it could be interesting or not. If you haven't thought about that.
So first of all, sorry for not defining all my acronyms. I hate when people do that.
I think you mentioned before about that.
Yeah. So VOR is the vestibular ocular reflex. It's basically it's a very sort of low-level gaze stabilization reflex. Mike Land has shown that it's as old as vision, and basically it's your vestibular organs. People call your inner ear. There's some pathway. And when you detect head rotation, your eyes counter-rotate. So if you look at a person and rotate your head around, my eyes stay fixed on you, my head moves around. It's because my vestibular ocular reflex is sort of counter-rotating my eye to maintain that fixation. As has been pointed out, it is not as simple as that, because depending on how far away you're looking, the gain changes. How such a low-level reflex is modulated by something as high level as what am I looking at is one of those questions. But yeah, VOR is the way that, and you can see VOR here because I'm fixating points in the world, but because I'm moving towards them, that fixation is not flat, it's tilted. So this is a hallmark of VOR in a gaze trace. Your second question was inverted pendulum, yeah. I think that generally the way that I think about that kind of stuff, because I'm more on the vision side of the fence, is I like the inverted pendulum model because it's so simple. There are people who don't like it because it's so simple, but I think that it defines a lot of the sort of the basic forces that are going on when you're just walking around like a biped. And so I think about it in that as sort of a proxy for when you're putting your foot on the ground, you're trying to shape the forces that define your trajectory, and the inverted pendulum is a nice way to think about what those forces are. I don't think this would have anything to say about the right and wrong way to model walking, but I do think that the way that you model walking tells you how you would use this information to control your movement. And something like an inverted pendulum saying, oh, like, you know, if your velocity vector is here and you put your foot some specified distance in front of it, if there's some critical point that will sort of bleed off all the velocity to bring you to a stop. If you put it this way, you'll veer off that way. And that sort of, the consequences of putting your foot here versus there are dependent on the model of walking that you use. And given that you're trying to use visual information to shape those forces, that's, I think, what that relationship is, if that made any sense at all. Yeah?
After you decompose the optic information into the retinal flow, it was like getting closer to the very primitive and basic way of controlling the movement. But have you considered any parameters for the retinal flow which would correlate with efficiency of such a gait, such as rate of error, rate of erroneous steps, and the average velocity?
Yeah, so I think that's getting back to sort of, looking at it's hard to define what efficiency means, particularly in a complex environment like that. One could imagine, if I had perfect knowledge of the full physics of the body and the full three-dimensional model of the ground, and VO2 and all that kind of stuff, you could measure efficiency. One of the basic assumptions I have is that humans try to walk as efficiently as they can in most environments, given constraints. But those kind of assumptions are often based on straight walking on a treadmill. And it's sort of an open question about how much or whether they apply to walking in these types of environments.
I was getting a little bit more about the retinal flow after processing. Are there any parameters in the resulting data that would correlate and eventually probably enable to predict the efficiency or maybe the velocity of such one?
I think the data's there. It's a very rich data set. And it's always just kind of how much time do you want to spend trying to extract that kind of thing. I think that the behavior is very rich. The relationship between gaze and footholds is very robust. And I think it's just a question of how clever you are at data mining. But I think that the kind of questions you're asking could be extracted from it, yeah. Particularly with the videos associated. I don't know how I would do it, but I think that is sort of on the class of questions that one could ask of this data set.
Yeah. So someone, I'm first.
You go first.
You have finally.
Okay.
So just sort of, it's been in the mix. Vision serves the planning of action, but maybe the action is there to have a cost function defined in the visual field that then constrains the action or determines the actions you take. Could you, and I'm thinking of the old story about the pigeon and its back and forth movement of the head, which is meant to stabilize a gaze. So what could be, other than having a smooth expansion, smooth expansion, what could be in your more detailed analysis be that cost function that locomotion serves to optimize?
Yeah, I mean, there's always kind of this chicken or egg stuff with this kind of thing, and it's often, I generally assume that it's some form of bootstrapping where it's going to be some bit of both. So, for example,
just for the heck of it, just turn the spit around for
yeah.
sake of argument.
So one of the things I've often wondered with looking at these sort of scan paths, do you look ahead for where you wish you could step and then alter it if that place is not available? Or do you look ahead at a place that it seems like a likely place you could put your foot and then choose from among the available options? And that's something that you know, if one believed that you could have a model of preferred gait cycle and then use that to project, here's your preferred foothold location, and then use that to analyze these scan paths, that might be a question that you could answer with that kind of thing. But I think it's a question, does the visual environment define your gaze pattern and then you step according to those constraints, or does your preferred gait cycle constrain your gaze behavior and then you sort of make it fit with the environment? And I think the answer is going to be probably both. Yeah. And I think that, you know, thinking about the sort of the perception action cycle and sort of coupling between the agent and the environment, and that sort of, you know, all those two-way streets that come out of that way of thinking is just going to be, that's the right way to think about this kind of stuff. Those aren't easy problems, but they live in this data set. And it's just a matter of being clever enough to extract them.
So just to clear my mind, so in that curl and divergence figure you showed, so a lot of that color shading that we get in the curl and divergence is partly when you're projecting into the eye coordinate or the retinal coordinate with the curvature involved in it. So that is kind of implanted into that color shade. And now somebody there in your lab, or you must have thought about the information between the center of the curl field, center of the divergence field, and the magnitude of the curl field, the magnitude of the in this code. I mean, there must be something we are extracting from it. Have you thought of that?
This is all extremely new. So it's a spherical pinhole camera model of an eye. We just talked to Dan Brainerd, who's a vision scientist who's developed a more complex model of the eye that I think could probably be like sort of tacked on top that has sort of a lens and all that kind of stuff. The space of things you could do versus the space of things I have done is a very different scale. I mean, this video, I mean, you guys are literally the first people who aren't in my lab that are seeing this stuff. It's not particularly, so congratulations. Thank you for watching it. But yeah, I mean, I've done almost nothing in terms of that kind of stuff.
Robotists who have their eyes planted who are super interested in thinking.
Yeah, I would.
How many roboticists are doing eye movements?
I don't know. Not many.
Yeah. Just one other suggestion. I mean, to that point, if you bring in the idea of cortical magnification and the splitting of the visual field into the hemispheres, particularly with your curl, you're looking to the left, you're looking to the right, you get, I think, some just qualitative.
Yeah.
Like you can just do.
Yeah, and that's one of the, for the non-vision people in the room, that's one of the sort of one of the nice things about thinking about things like this is your visual cortex is mostly organized retinotopically, and there's been a lot of sort of talk like, well, if it's head-centered flow, then you must have these coordinate transformations and yada yada. But being able to put this back into a retinotopic reference frame makes it much easier to connect it to the way the things that we know about the visual cortex. And one of the things I've been doing in the past year is setting up conversations with people like Alex Huck and Larry Cormack, who do monkey electrophysiology and motion processing and macaques and marmosets and things like that, to look at those kinds of questions, and specifically, looking at things like this relationship between stereo information and motion information, and sort of how those are processed and this, that, the other. Carl's been doing a lot of stuff of looking at, sort of putting sort of receptive fields onto this type of data and seeing things like that.
The easy win, when you talked about curl, right? The curl calculation telling you, is my path just to the left or just to the right of it, right? Where you're looking, that information is going to literally split in your hemispheres in V1 and
I see what you're saying.
and I mean.
Right, because of the visual field versus the retinotopic location. And
that's a huge win, quite apart from receptive fields.
Right, yeah, because that would pop out. Yeah, thank you, yeah.
I think we're all happy.
Thank you.